instability of flame, which is the basic instability of a flame. The basic instability is due to hydrodynamics, which is coming from the fact that the flame is a quasi-isobaric wave, so that the density, because P is the same, rho T is the same on both sides, so T is different, so rho is different. So the density of flame, you know, it can be viewed as a wave with a density in the burned gas much smaller. There is something here, I don't know. Much smaller than in the fresh mixture. And this is going to develop a strong instability of flame called the hydrodynamic instability of flame. So let me start with first to develop the jump across an hydrodynamic discontinuity. We consider the flame, for studying this hydrodynamic phenomena in a flame, we will assume that the flame is very thin compared to all the other lengths in the problem, essentially the wrinkles of the flame, the wrinkles of the flame. So in that sense, you see, one must, for the validity of the theory, one must have a wavelength all the time much longer than the flame thickness, because we are going to consider the flame as a zero thickness discontinuity. And as you will see that there is a limit to that, but let's start to work in this first limit, where the wavelength is very long. So you start with mass conservation, and I wrote now the problem in 2 or 3 dimensions. So the capital letters are vectors, and the gradient is a vector. And so you have the mass conservation, momentum, conservation of momentum. I forget about viscous effect. I will explain you at the end why it cannot be important in this problem. And yes, when you put everything together, you can write the momentum, the Eulerian derivative of momentum, like a divergence of a tensor, a unity tensor for the hydrodynamic pressure, the thermodynamic pressure, and you have the tensor coming from U grad U, which is called the Reynolds tensor, in fact. Not the Reynolds, excuse me. It is a tensor which is due to the U grad U. I don't remember the name of this tensor. So now we are looking for a tilted, to begin with, for a tilted plane of front. So here are the capital R is I will work in 2 dimensions to begin with. So X will be perpendicular to the flame, and U will be normal to the flame, and W will be the tangential component of the flow. So now we are going to neglect the curvature effect, which means that all the tangential to the flame are negligible. And this is one of the basic approximation. So your equation reduced to this equation here. And now, if you want to look to the jump, you assume that everything, that the inner flame structure is steady, so that this term on the left-hand side are 0, And then in order to obtain the jump, you just have to integrate across along the normal. And this, if you integrate, and we are lucky because on the right-hand side, we have only gradient along the normal of quantities. So in such a way that the integration is trivial. So you integrate the mass, rho u is the jump of mass flux is the same on both sides. And momentum tells you that P plus rho u square is the same on both sides. And then you have the jump of rho uv is the same, is equal to 0, but because rho u is constant, you obtain that the jump of, there is no jump in the tangential component of the flow velocity. So one can also realize the following, that when I suppress these transverse quantities, it is because if you integrate that across along the normal, okay, you obtain something which is proportional to the thickness of the discontinuity, called dl. And because dl go to 0, as soon as that you integrate a quantity which is not a gradient, because if it is a gradient, this is going to give you a jump. But if it is not a gradient, when the thickness is going to 0, you obtain 0. And this is another way to realize that these transverse gradients are not important in the jump condition. So you obtain this jump, and you see what I have written here. Here you have that it is 0 because the laminar, because the thickness is going to 0. And now if you have a gradient, it is not 0. That's the main point. Okay, this is the only point. This explains you what are the jump across a flame. Let's say a planar flame which is tilted. Okay. So this is a summary of what I said. Because of the jump, that remember that the normal velocity, the velocity relative to the flame in the normal direction has a jump which is associated with a jump of density. So you have this is in the normal. The tangential are conserved, so you have a deflection of the flow velocity of the flow, okay, of the streamline. You have a deflection of the streamlines across the tilted front, okay, and without any calculation, this could be enough to understand why you have an instability, a very strong instability. Look at my picture on the right. I have a wrinkle, the flame, and I look to what is going to happen. If you assume to begin with that there is no change of the, not in this picture, but assume that there is no change of the flow ahead. That's in the fresh mixture. Assume that. Now, because of the deflection of the velocity, you will have a deflection of the streamline like that. Exactly, because following this law here, conserving the transverse and so on. Now, because the transverse velocity should be constant, you also have, you also have a modification of the streamline ahead. So this, in a sense, is difficult to understand. That as soon as you wrinkle a flame, you change the flow upstream and downstream. Downstream is okay, I understand very well, but also upstream. Okay? This could be difficult to understand because you can ask, what is the mechanism propagating this information that I have wrinkled the flame ahead? This is a sound speed. But because we are in the limit of a very small Mach number, this sound speed is infinite, excuse me. So you have an instantaneous modification in the low Mach number limit of the flow upstream the flame in the fresh mixture. And now, with this picture in mind, look at that. Now, you see, you have the streamlines like that. Because you are incompressible behind and ahead, you are incompressible, okay? Low Mach number approximation. In that case, you see, because the streamline have this direction, you have a flow here in that direction on point A, the burn gas flow, which is smaller than at infinity, just to conserve the mass, okay? And it is just the opposite in B. The flow in B, longitudinal flow, is larger than at infinity. But remember something, that a flame, if its inner structure is not modified, want to see a flow relative to the flame equal to the laminar flame speed. But this is a constant. In such a way that to restore here the flame structure, the flame motion has to be the flame motion has to be on the left and here on the right. So you are going to, as soon as you wrinkle, any initial wrinkle are going to be amplified. And this is a hydrodynamic instability, which is easy to understand looking at this picture here. Now, most difficult is to develop a quantitative analysis of that. It's not very, very difficult. It is technical. I will do that for you, just as an example of this is a calculation that has been developed around the 1940s, by a Frenchman called Darieux. He was an engineer. Maybe you have heard of the Darieux, how do you call that? The wind Darieux, you know, yes. I don't remember the name. Éolienne, how do you say that? Okay. When you go to the west coast, you will find a lot of this éolienne. I don't know what it is. The working with the wind, which turbine, which have a vertical axis. And wind turbine, no? And this was invented by this man, Darieux, a French man, in the 38. But Landau developed the theory independent. Darieux did not publish it. It was published in a crazy journal. Nobody looked at that. And Landau developed the same analysis later on after discussing with Zeldovich about the flame. And he was concerned by Landau by this instability. So this is called now the Darieux-Landau instability in the literature. So I will use the following notation. My horizontal axis will be X perpendicular to the unperturbed flame, and the transverse axis will be called Y. So the equation of the front, when it is not strongly disturbed, could be written like an equation like that. X equal Y equal function of Y and X alpha function of Y and T T is the time, and y is it. So this alpha is simply the displacement of the flame on the x-axis, which is not the same depending on y. It depends on y. Now, the flow velocity has two components. I work in two-dimensional. This can be done in multidimensional, but in three-dimensional. But okay. Now, another point important is that you are going to work in the reference frame of the unperturbed planar flame. Okay. So now, and it is not. No, I say something wrong. The unperturbed planar flame is x equals 0. Now I am to work in the reference frame attached to the flame. So I will change my coordinate x by x minus alpha. Now, with this just a few geometrical relation, when you call alpha dot y, not alpha dot, alpha prime y, the derivative, the tangential derivative of the longitudinal displacement of the front, it is d alpha over dy. The component of the normal is 1 over square root 1 plus alpha y squared, because the normal its norm is unity. This is why you have this square root behind, minus alpha prime y divided by square root of 1 plus alpha prime y squared. And now, the normal velocity relative to the front is the flow velocity minus alpha prime y. The W is the tangential velocity and divided by square root, and the transverse velocity along this, okay, is this one. Yes, the transverse velocity in the initial frame x, y, and now because you are working in the reference frame attached to the wrinkle frame, you have this alpha point 1 you have here. So now you have this. And the normal velocity of the front, which is the propagation, the velocity of the front in the normal direction, called capital D here, F is for front, is alpha dot T, d alpha over dt, square root of 1 plus d alpha over dy square. That's all. This is simple geometrical consideration. Now, if you look to the normal component of the flow relative to the perturbed front, you have un minus df. Un is a normal component of the flow velocity minus the normal flame velocity. This is the normal component of the flow relative to the front. This is what you have to consider to use the jump condition. The jump condition are defined relative to with flow velocity relative to the front. Okay, so this is the normal component. The tangential is the same as in the initial laboratory frame. There is no change in that because in the linear approximation at least. And mass conservation tell you the minus will be in the unburned mixture, plus will be in the burned mixture. The overline is for the unperturbed solution. Because I am working in the low Mach number approximation, the density is not modified by the wrinkling. This is going to be different if I take into account the compressible effect. But for the moment, I do not take into account the compressible effect. So the density on both sides is the initial density for the planar flame, unperturbed plane. This is the conservation of mass. Conservation of momentum, it is written here. I have recalled that just before. P plus rho u square is the same on both sides. And this now, using the expression of the normal velocity, which is here, you obtain this relation. This is for the tangential conservation, conservation of the momentum in the transverse direction. This tells you that the relative transverse velocity is conserved across the flame, which is written here. So on both sides, the denominator vanished, is simplified. So now you have the three boundary condition across a wrinkle flame. It is written here. That is a pure geometrical thing. There is nothing complicated. Now, what we are going to obtain is the motion of the flame. How the flame is going to move. I gave you a physical interpretation of how it is going to evolve. That but now I want to go further and to be quantitative. So I begin to linearize the Euler equation of incompressible fluid on both sides. This is the first is a conservation is a mass conservation in incompressible, divergence of the velocity zero. Delta is a perturbation relative to the mean, not the mean, to the unperturbed solution. Overline is the unperturbed overline MF is the unperturbed mass flux, which is the same on both sides. And now if you go back to the equation in the reference frame of the flame, you obtain this is conservation of mass here, conservation of the momentum, longitudinal transverse. And the delta pi is here I have incorporated in the pressure the effect of an acceleration normal to the front. This is because I want to consider flame propagating downwards in the tube or upwards. So in both cases, you have an acceleration which is perpendicular to the unperturbed flame, okay? I keep that here, just because I want to solve this problem. Now, when you combine these two equations, it's very simple. You take the derivative with respect to the longitudinal component here to the longitudinal component. You use the conservation of mass. This is going to be 0, and you are left on the right-hand side with the Laplacian of the pressure which is renormalized by the acceleration, but this is not very important. You can, to begin with, forget this renormalization. So you know immediately what is the equation of the perturbation of the pressure on each side. It is Laplacian equals 0. Very good. Very simple. Now, if you want to go further, you want to obtain now the flow velocity, not only the pressure. So you use the Fourier decomposition. So here is the equation of the front, and you use a decomposition tilde. You say tilde alpha t exponential Fourier decomposition I k y. K is a wave number, the inverse of the wavelength with a factor 2 pi. And this, and what I did not write here to simplify the notation, this tilde alpha is also depending on the wave number. It's depending on k also. But to simplify the notation, I did not write that. Now, this is written here. The Fourier component depends also. There is a mistake. Depends without S. Also on K. Okay. And now for a field, the Fourier component not only depends on time. The transverse velocity is in the exponential. This is a Fourier transform, but it depends also on the longitudinal component. When you have a field, here you have for alpha there is no, because the alpha is x equal alpha y. So there is nothing in alpha. There is no x. Good. So here is a summarize. Is a summarize of what I have just written before. And now I use the Laplace equation. When you take the second derivative on the transverse direction, this is going to put in front of the Fourier component k square, because when you take the gradient in y, you have when you take the gradient in y, you get down ik once, multiplied by ik, it's minus k square. So this is simply the Laplace form of the Fourier transform of the Laplace equation for the pressure. So you obtain immediately, when you in Fourier transform, you obtain immediately the solution. The solution for the pressure is going to give you the pressure here, time t, on both sides. It's either burn gas or flame mixture. Time, what? Exponential something minus modulus of plus or minus modulus of k. And the value of f here is the value of the component on the unperturbed front. Okay? This is the solution. Now, for the flow velocity, you use the same Fourier decomposition here, which is written here. Here are the equations. The mass conservation now takes this form, where U is the normal component of the flow, tilde is a Fourier transform. Every tilde quantity depends also on K, but this one depends also on X. And here is this is the Euler equation. And you see that the pressure appears as how do you call that in English? A given a forcing term on the right-hand side of the flow velocity. You see, I have what. Keep in mind that I have linearized here. So, in order to linearize, I use the unperturbed flow in front of the longitudinal. Longitudinal derivative. Okay, across the flame. This is the unperturbed flow. You have this. So you have now here you have the equation for the flow velocity and where the pressure appears on both sides as a not on both sides, on the right-hand side as a forcing term for the flow. Okay. Now you have to consider this equation here that I have just written before. And depending, the plus of minus depend on the plus of minus here. And this plus of minus is going to be defined for the pressure, for the disturbance of the pressure to be finite at the infinity. So let me be back to be sure. You know, what I require is that for x going to plus infinity, which is for x going to minus infinity, the perturbation of pressure cannot diverge. This is constraint that I impose to my problem. In that case, you select the plus of minus depending on the side you are, because here is the modulus of k. So when you are for positive, you should have minus modulus of k, and when you are negative in the fresh mixture, x going to minus infinity, you should choose here the plus sign. Okay. Now, if you have this equation, this is a linear differential equation that you have to be solved with let's say it is a known term on the right-hand side. This equation, what you are going to do is that the general solution of such a linear equation is given as the general solution of the homogeneous problem without the right-hand side, plus a particular solution of the full equation, as usual. This is a mathematical result that you must know when you do your mathematical class. So any linear equation like that with a forcing term, the solution is a general solution of the homogeneous problem, that is with this equals 0, plus a particular solution of this 3. So it turns out that this solution is going to be decomposed in two parts. One is a rotational part, and the other is going to be a potential part. And rotational part is the R here is to recall that it is the rotational part, and the P here is to recall that it is a potential part. Now, have a look to the homogeneous equation first. This equation is written here. Okay? The general solution of this equation is just a displacement without deformation. It's just the solution of that should be a function of t minus x divided by u bar. You see? If you are not convinced of that, you take this information. This is just the displacement without deformation. Take this, put it in this equation. The time derivative will give you a derivative of that, and the derivative of x will give you a minus times the derivative, multiplied by divided by u plus, so and in such a way that the sum is 0. So your rotational path you obtain is simply, that is very simple in the linear approximation, is a propagation of vorticity by the flow, by the unperturbed flow. Okay? This is very simple. Now, and so you are going to write, so in such a way that in ahead of the front, because there is no vorticity at infinity, ahead of the front, because the flame, the flow is uniform ahead of the front. In that case, the rotational part in front of the flame in the fresh mixture is 0. And on the burn side, it is given as an unknown function here u tilde u p r plus, which is a function, in fact, as of t propagation without deformation. And this, so you have an unknown here. You have one unknown, which is a function, an unknown function of time, which is u tilde plus small r. This is a general solution to the homogeneous problem. Now you have to find this, but you know the form. Now, look to the particular solution. In order to look to the particular solution, to obtain the rotational part, I was working with the original variable. Now, to find out the particular solution of the complete problem, I am going to work with the Fourier transform. So you look for a particular solution of the form, which is written here. The capital P is the initial field, and the small cap u and the small p is a function depending on time only. And time, you look for a solution like that. Let's see if the solution like that is going to be solution of this equation. It turns out that this is the case if you if you put this in here, you are going to obtain the form of u tilde minus, like an exponential function, unknown function of time, an exponential of kx normal. Okay, normal. Okay. How do you say it? Well, okay. So now you find out that you are going to have a similar thing for the burn, but with a minus k here. I did not write that. So you end up to find out three unknown functions to obtain the solution. And these unknown functions are going to be given by the jump conditions. Okay? Now you have to apply the jump conditions. So here is, again, the equation. In the unburned gas, you have this equation. In the burned gas, you have this equation. You see? But now, in the be careful. Where is yes. You see, in the burned gas, you have the rotational part that you have to add, which is here. This term are the particular solution, which is given here, and this term is the rotational part. And you have the three unknown functions, one here, the second one here, and the third one here. So you have three unknown functions to determine to obtain. Now you use 4 boundary conditions, 2 for the conservation of mass. You know, the mass, the perturbation of mass flux in the fresh mixture on the front, at the front, should be the same as the perturbation of the mass flux. This is conservation of mass on the burned gas. And you have 2 other for the conservation of normal and tangential components. So you have 4, and you have 3 unknowns. You can say, okay, there is one additional, relation, and this additional relation is going to give you the velocity, the evolution of the flame front. Because you do not have here evolution of the flame front. So now you have, and now the thing is going to become a little bit more technical. Now you have to apply, because you excuse me. Okay, you know the form of the solution, no problem. And now you have to apply this four boundary conditions. And this is a little bit technical. Let's try to apply. For example, for the mass, it is easy. Don't forget that you are working in the linear approximation. So all the perturbation you are considering should be linear. You reject every quadratic or cubic term and so on. You keep only the linear term. This is because you are looking for a small disturbance, and you are looking to how a small disturbance is going to evolve. Okay? Linear problems all the time are much more simple than nonlinear problems. So they may be technical as it will be here, but not. There is no problem, fundamental problem to solve a linear equation. So this is the mass conservation, linear mass conservation. Immediately you see that the perturbation of the function f, that you found immediately that the perturbation of the flow velocity on both sides are equal. They are equal and equal to the derivative of d alpha over dt. That's all. You see. This is the two relations that you obtain. Now, you have to write down the tangential component. I will little bit skip the details. Here you have the flow. I have recalled the flow here. That now you have to apply this tangential component. And now you are working in Fourier transform. So the derivative, the transverse derivative of a quantity is ik the quantity, the Fourier component of the quantity. So now, if you use the mass conservation, you have this relation here between tells you what is, no, excuse me. This is the expression of the transverse derivative. This is the expression on the there is something wrong here. No. No. This is a conservation of mass, and this is a conservation, what is it? du over dx. What does that mean? Also is a conservation of mass. This is a conservation of mass in front of the flame. This is a conservation of mass behind the flame. So you have these two relations. So you put that together, you obtain that. I will now. So now you have this three. Now you see just what you have to realize, that you have the three unknown of the flow plus the unknown tilde alpha for the front. and I have 4 relations for 4 unknown, so I'm going to determine everything. Okay? So you just play with the first, excuse me, you just play with the first, you eliminate here this, skip the detail if you like, I don't. Normal component, this is a tangential component, a normal component. The normal component is very easy. It tells you that the jump, that is important, that the pressure on both sides of the flame is the same. The pressure is the same on both sides because the difference is coming from nonlinear term. You kick them out because you are working in linear approximation. And now if you work with the tilde pressure, which is incorporating the acceleration of gravity, you have this relation here. Now, you put together that, I skip the detail, and you obtain a linear equation for the Fourier component of the wrinkle flame. The Fourier component of the wrinkle flame is, it is written somewhere. No, it's not. Yes, yes, it is written here. You see, you have the Fourier component here. You obtain a second order differential equation for this Fourier component. All the other things in this equation are known. These are the unperturbed density. This is the unperturbed mass flux across, across the flame. This is the acceleration of gravity. And K is the wave number that you are considering. Don't forget that in every Fourier decomposition, the Fourier amplitude tilde depends also on K. I did not write that to save the notation. Okay? So the K is given. You consider a wrinkle which is given, and you look to what is going to be the evolution of the flame front for this wave number, for this wrinkling. And you obtain this equation. It's a simple equation. And simple equation is a sense that it is an ordinary differential equation of second order with constant parameter. You cannot dream of simpler equation for the dynamics. See, yes, you can. The simplest one will be without the second derivative and only with the first derivative. Here you have a second derivative. And now, let me summarize. So here is a Fourier decomposition of. Now I have put the x in the vertical because my gravity is going to be in the vertical direction. So I have turned the axis for p over 2. Okay. So the transverse direction is here. This is a longitudinal direction. Burnt gas. I put burnt gas on the top to begin with, and the fresh mixture, which is much heavier below. And you have the wavelength. And then you have an amplitude, which is given here, which is the Fourier amplitude, and you have this equation for the Fourier amplitude. What are the parameters? Once again, you have the mass flux, which is essential in flame. This is the characteristic of a flame, is that you have a mass flux crossing the flame. And you have then this. you have the wave number, which appear here and here. And also here you have, in addition of that, the effect of gravity. Okay? Here's the equation. Now, let's start to analyze what will be the result for a passive interface. Passive, you say in English? I don't know. This is a flame, an interface without flux crossing the interface. For example, it is the interface between air and water. Okay? For example, you neglect the vaporization, and so in that case, you have an interface across which there is no mass flux. Okay? I start with this, because this is going to describe a well-known phenomena of Rayleigh-Taylor bubbles and so on. So in that case, the equation that I've written here, because the flux crossing the flame is 0, the equation is very simple. You have a second derivative here, which is equal to gk times the jump of density. That's all. This is the result for what is called a passive interface, linear equation. So now, to solve this equation, let's start to use a normal mode analysis. That's looking for an amplitude of the Fourier transform in terms of an exponential of sigma, and sigma here will be the real part of sigma will be the growth rate or the growth damping, if it is negative, of the amplitude. So you looked for a solution like that. This is called a normal mode analysis. Why normal mode? Because this sigma is going to depend on k. So and then you have the, oh, excuse me. Now you look for this, and if real sigma is negative, the front is stable, which means that the amplitude is going to be back to 0 when the time evolves. And if sigma, the real part of sigma is positive, you are unstable. Up, the amplitude are going to grow. Okay. And this is the well-known Taylor instability. Assume that G is constant, the acceleration is constant, and the Taylor instability is when this quantity is positive. The difference of this is positive. In that case, you have sigma square. It equal to what is called a Atwood number, which is the let's say simply the jump of density normalized without dimension. It's called the Atwood number. And so you have now that sigma that you obtain here, you have a term which is square root of this Atwood number, gk. And this is going to tell you how the initial wrinkle is going to, to develop when the heavy fluid is above the light one. You see? This is called the Rayleigh-Taylor instability. And it's, what is very interesting is that now this is a linear analysis. It's not a difficult one. This is for students. Now what is difficult is to do the nonlinear analysis. When the amplitude becomes large, what is going to be the fate of this amplitude? And now this has been studied, a large number of studies in the last century, and you have a form of a bubble like that, and you can find out by a nonlinear analysis that the bubble is going to grow up. You know, bubble, the gas is here, the liquid is above, and this bubble is going to propagate upwards at a velocity which is proportional to square root of gr. R is the radius of the tube, which is going to give you which is essentially the wavelength. But now it is a nonlinear thing. So now if you do just the opposite, that now you have the light fluid above the heavy one, and gravity like that. Now you obtain this is negative, so you obtain this this is going to negative, and you obtain that sigma is purely imaginary. What does that mean? Is that you have an oscillation that is described here. This oscillation, wait. That's, this was known already by Newton, 7th century. He found this oscillation, the wave oscillations. He found the result by a simple analysis. Newton. Not easy to follow. What he did, I can show you. It is interesting. You know, you want to see what are the waves, what is called a gravity waves, how these waves evolve. So you have air here, water behind, and you want to know what is the motion of that. It is oscillating, as I show you. And what he did, Newton, is this. Take a tube in you, and he put liquid in it, and he was looking to what will be the oscillation of the thing without you forget about the dissipative effect, and he found out this result already. So, 17th century. Oh, you see. Now another problem, very interesting, is when the gravity is oscillating. Now you end up with the equation which is written here. You see this equation. This is called the Mathieu equation, which was studied last century. Yes, Mathieu's, maybe end of 18th century. I don't remember. No, I don't remember. So this equation, I will discuss that when such an equation, when I will discuss, if I have time, a flame propagating in a tube. Okay, do you remember the picture I showed to you? And this equation, because this term here is going to be the model of the acoustics. Acoustics, you know, if you have a longitudinal acoustics wave in a tube, the flame in the middle is accelerate and decelerate in an oscillatory way because of the acoustics. And now this is the equation you have to solve. Okay. Let's say 15 minutes breaks.